organizers for inviting me to give this talk. For the sake of contrast, I will speak slower. To introduce this project, I recall the series of conversations I had with my friends, an architect and a designer, about the time when Anfa announced this research program. The architect is Greg Lean, who is a professor of architecture and urban design at UCLA, and he's a practicing architect. Greg Lean Forum is his architecture firm. And my designer friend, a narrative designer, is Alex McDowell. He's a professor of art practice at the University of Southern California. Our conversations concern mostly the present state of the art and the disciplines and the future. Very briefly, for Greg, the architect, the present practice of architecture is defined by excellent insight into the spatial character of buildings, mainly because we spent several hundreds of years perfecting our insight into representation of spaces using linear perspective and similar tools. The future for him depends on our ability to develop an equally advanced insight into the dynamic character of experience. Not only the experience of a person moving through the environment, but also because modern buildings quite often involve moving parts, and also because we want to better understand how to represent built environments in immersive spaces. For Alex, the present was defined by visual narratives. He's a filmmaker. He spent more than 30 years designing films like Minority Report, Terminal, with Steven Spielberg. He created sets on large scale, but those sets were represented on flat screens. So in every case, visual narrative was screen-based, and the spectator was static. For Alex, the future depends on our ability to let audiences enter the narrative using immersive environments and environments that mix digital and physical components, such as augmented and mixed environments. Now, as we discuss these concerns, we realize that from both perspectives, from both domains of represented space and physical space, they face the same challenge, which is a need to model the structure of spatial experience in solid space, similar in power and generality as perspective, which we enjoy as one of the most important tools for representing space for almost 600 years, counting from early Quattrocento, roughly 1420. So we want to develop a model similar in generality and power for solid, three-dimensional, volumetric, immersive space. There are many ways to enter this discussion. For me, one of the easiest ways to introduce this vision is to cite a Gestalt psychologist, German-American Gestalt psychologist, Rudolf Arnheim, who in the 1970s presented his vision of dynamics in architecture in this book called Dynamics of Architectural Form. In this book, he used this drawing that I show on the right by Italian architect Paolo Portoghesi. This drawing shows a plan view of a built environment. So these thick lines, suppose, represent walls of buildings or a garden, and the concentric circles represent the effect the environment has on you as you move through the environment. Arnheim cites Portoghesi, and he writes about it in the following way, which is significant for my talk today. So here is what he says. In perceptual experience, the spaces surrounding buildings cannot be considered empty. Instead, these spaces are pervaded by visual forces generated by the architectural structures and determined by the size and the shape of their generators. Next, these visual forces, they must be understood as components of perceptual field that surrounds buildings. And lastly, a field of visual forces expands from the center of every generator and propagates its wave front as far into the environment as its strength permits. So this view is remarkable because it captures some very clear intuition about what we may call the structure and dynamics of experience. For example, as a person moves through the environment and she enters different parts of the environment, her experience could be described as a field. This is sort of a precursor of thinking about experience of large spaces as a quantitative field, even though this particular illustration is certainly not quantitative. And yet, the idea that a perceptual field has a wavefront would strike scientists as perhaps too speculative. Nevertheless, I like to use this illustration because I believe it contains a seed that can be developed and brought into fruition using the tools and ideas of modern neuroscience, and this is essentially what we attempted to do in this project. Now, to introduce this modern vision of experience, I'll use a piece of modern art. This is a painting from Salvador Dali. It's called Gala being his wife, contemplating the Mediterranean Sea, which at a distance of 20 meters transformed into a portrait of Abraham Lincoln. This is the actual title of the painting. Now, depending on where you see it, you may see different things. When you see it up front, you probably see a woman here in the center of the painting. If you're sitting farther away, you probably see Abraham Lincoln's portrait. Now, this is, so I'll go back and forth. If not seen it, it's very entertaining. Now, why does perception change as you move closer or farther away from the painting? There are two reasons. First, our vision is not equally sensitive to different features of the world. And the way our vision is sensitive or insensitive to certain features of the world is very well understood by modern vision science, although in very restricted conditions. Second, the amount of detail, visual detail, projected into the eye depends on the viewing distance, which is why sensitivity to features depends on the distance. Now, how does it apply to experience of built environments? So here's one example of an urban scene, and as you explore it, you will discover that the amount of visual detail certainly changes, and it's a part of the sort of bodily change, a part of the makeup of the environment. It also depends on your distance to the environment. For example, the features that appear closer to you are separated by larger distances than the features that appear to be farther from you. Now, if we knew exactly how visibility of features depends on the distance, we would have a beginning of insight that would allow us eventually to construct such a quantitative map that Arnheim and Portuguese proposed. So one way to think about it is that I use a metaphor from neuroscience, visual neuroscience, where we think about representations of the environment as maps. So for example, this scene is represented in the brain in the form of multiple maps, of which I showed just two, where I simply took, I filtered this image, and on top, on the right top, I show only regions of or parts of this image that contain high density of detail or high amount of detail. Let me put it simply, amount of detail. And on the bottom, I show only parts of the image with a low amount of detail. Then you could see certainly that here, for example, this tree on the back is captured by this map and not that map. It so happens that the brain allocates different amount of resources, number of cells to different maps, which is why we are capable to see certain features better than other features. One common illustration of this, which everybody could experience, is this panel introduced by Campbell and Robson yet in the 1960s. So here I vary two things. Amount of detail changes from left to right, and the contrast of the image changes from top to bottom, increasing top to bottom. Now, when you try to find the boundary between visible and invisible features of this chart, you will see this curve. So probably you don't see much of the modulation of luminance here, and you see it more to the top. So this is an example of how amount of detail dictates your ability to see the detail. Obviously, if you take a pattern that doesn't change in the amount of detail and simply move it away from your eye, the projected amount of detail will change. So going left to right in this direction is equivalent to taking a pattern with fixed amount of detail and moving to the right. Here I try to capture it in the next slide. Let me just go there straight. So here is Here is the pattern with fixed amount of detail. I move it away from you. And for example, this contrast here corresponds to this dashed line, which means that at this contrast, for projected low density of detail, it will be invisible. It will become visible as I move it away and invisible again. That is, there is a region in space here marked by gray on the bottom where this pattern will be visible. So you could think of that as a solid region, three-dimensional volumetric region that makes access to the pattern possible. So essentially, this is the beginning of understanding how to construct a quantitative map of the sort that Anharm and Portuguese proposed, and introduce it as a ring of visibility, more technically, a solid field of visibility. It's a simple metaphor and a powerful model that works like this. So imagine, again, this is a plan view of some environment, and this is something you want to see, a building or some feature, sign. Now, this arrow represents your trajectory in space. You're moving, driving along this trajectory. Now, here is my ring of visibility. You don't see it when you don't see the object of interest represented by the star when you get too close to it, and you don't see it when you are too far from it. So you'll be able to see this object as you traverse the part of space where you're inside the ring. Now, suppose there is another object represented by white star on the left. It has its own ring of visibility, solid region of visibility. Now, if I knew exactly how to capture this, the structure of this solid region, it's all the distances and thickness in quantitative detail, I would be able to predict where the two experiences are possible together. For example, this darker region represents the overlap of two regions of visibility, and this is the beginning of predicting, of experience of space in terms, for example, of where you could jointly experience object A and B, or maybe not experience certain objects. You could, if you had this algorithm, for example, in your computer-aided software, you could design things such as include or exclude things from the environment. So back to this map, quantitative map, our project was to begin mapping out the solid regions of visibility to prove that this mapping is possible. This is our title, the project that we did with funding from Academy of Neuroscience for Architecture. We called it Vision Science for Dynamic Architecture by vision scientist, a kinetic architect, and a narrative designer. Very briefly, our goal was to translate experience of patterns, visual patterns, from two-dimensional mode of rendering, which we call cinematic mode, to three-dimensional mode of rendering, which in our hands looked like this. It so happens that UCLA Department of Architecture a few years ago established an architectural robotics laboratory. They obtained a number of large industrial robots. We used them to do something very simple. We mounted a projector on one robot and a screen on another, and we moved the two together, trying to map out solid regions of visibility while we presented patterns on the screen. So it was the main challenge in the project was to design the software that was capable of presenting images and moving the robot synchronously. And effectively, it looked like that. The subject was seated in a large space, in dark room or illuminated room. A periodic pattern like this was presented on the screen, and the robots were moving both the screen and projector at a fixed distance between the two, so the amount of light would not change. So here's an example of subject sitting, looking at the screen, approaching the subject, going back and forth. Now, a short digression of the many patterns we could use. We use patterns that are shown here on the top row, simple periodic patterns. It so happens that limits of perception for great variety of patterns, for example, those shown in this family, they all captured the same law, the same simple function I showed you a few slides ago with the chart of visibility. Here's another example. Letters, for example, if you change the density of detail, as I showed before, in a slightly different way, you see the same pattern. So the law, which I show only in images, but which is known to us in mathematical detail, it applies to great variety of images, which is why by measuring perception to the simple patterns, we could predict experience to much more complex patterns. So very briefly, here is the method for one of the experiments. Here I show the distance from the eye to the screen, and here's the time of response of the subject. The robot moved the screen towards and away from the eye. Every second, the computer would emit a signal, and the subject would report her response. It was whether I see it or don't see it, or I see it move left or right. So we used different kinds of report, direct report and correct incorrect report. Just to illustrate how the results look, as you move the same pattern that doesn't change away from the eye, viewing distance and projected amount of detail, of course, correlate. So in this example, if you use certain low contrast, you increase viewing distance and so increase projected amount of detail. You go from the state of invisibility to the state of visibility over the distance of something like half a meter. And this is a remarkable result for our mission because it suggests that indeed those rings of visibility that I was talking about, they exist, they could be mapped out and predicted from our models. Just one more example. If you slightly change the contrast, you could expand the region of visibility. You could move the boundary between visible and invisible towards the observer or away from him. So this is an example of how when you design immersive environments for virtual architecture, for other experiences, you could actually engage the user, attract his or her attention to a feature by subtle manipulations of contrast. So to summarize, this is, I believe, the first time in the history of both architecture and vision science where we mapped a solid region of visibility. We used the quantitative model. The way I like to introduce it is in terms of invisible palace. So essentially, a space like this consists of regions which are invisible themselves, but they are real, like rooms of an invisible palace. As you enter this room, you're exposed to certain experiences. When you're outside of it, you are not. These regions of visibility could overlap or nest in one another. And essentially, this is the first step towards describing that structure, that invisible palace, quantitatively. Now, to sum up, this work was an interaction between a vision scientist, architectural design, and narrative designer, and I think a great number of different disciplines and sub-disciplines could benefit from it, not only architecture. So some of them in architecture would enjoy the ability to predict experiences for architectural urban design, and also for design of tools for architectural design, where you could embed a model, a quantitative model that predicts experience into your software, and that experiment with amount of light, change of lighting, position of walls, etc. For narrative design, of course, it is also important as we bring in virtual, augmented, or mixed realities, where so many things move together. You cannot really experiment with it by trial and error. You have to use some sort of quantitative model to predict experience. I mentioned virtual architecture, and also the domain for which we call, for lack of better name, post-cinema, where it appears the movies of today are heading, where you become a part of the narrative, you enter the screen, and there you also want to predict where certain experiences are possible in larger space. So in conclusion, what happened over these 2 years since we completed this proof of concept, we explored applications of this idea with multiple professions, and just this year, about a month ago, we established a center called SPACE, which is an acronym for Spatial Perception and Concrete Experience at the University of Southern California. The word concrete is a portmanteau term borrowed from concrete mathematics. Concrete, as you may know, stands for concrete and continuous and discrete, which is a combination of experiences from a physical continuous environment and discrete stimuli from augmented environment. There is the website for the site. You're welcome to visit. And please get in touch with me if you're interested in any of the projects listed there. If I have a bit of time, I could talk about these projects. Just very briefly, using the metaphor of space, we divided the clusters of projects we are going to carry out under the auspices of this center, we divided them to so-called zones. There are 5 zones. The first zone, called structure of spatial experience, essentially is dedicated to continuing this kind of research, mapping out solid regions of visibility. Now, these solid regions, they have to do only with boundaries of experience. The next challenge, of course, to understand how information which is available in different solid regions of visibility interacts across space, and that's our second zone, which we called Gestalt in solid space. So Gestalt is Gestalt psychology, of course, has to do with combination of information that comes from different parts of the environment, how we experience larger structures from components, how they interact across space. That will be the focus of our second zone. Third zone, multi-thread experience. It has to do with the fact that actions that appear in different locations in the larger environment could drag your attention. We want to understand how attention changes boundaries of solid regions of visibility, how you could be attracted to one object to another in the larger space. This is the theme of the third zone. And the fourth zone has to do already with concerns of narrative design, where you want to actually translate narrative, for example, from a two-dimensional screen to immersive environment. So that's roughly the layout of our project so far. The fifth zone is called Museum of Experience, where we create interactive demonstrations for students in architecture, video games, and similar professions to take one of these examples and create interactive demonstrations in virtual or augmented environment. So I will stop here. Thank you so much.